Hello everyone, welcome to Professor Z Academy. Today we'll be discussing simple harmonic motion. So, to talk about the simplest form of simple harmonic motion, we need to talk about springs. So, springs, if you're not familiar already, are objects or tools that look kind of like coils, and when they're stretched by some amount, let's call this change x, they will then pull back into their original state. Furthermore, when they're pushed by a distance x, they will return to their original state. Basically, they want to return to equilibrium. These springs follow a law called Hooke's law, which states that the force that the spring provides on an object attached is equal to negative k, which is called the spring constant, times x, which is displacement. Now, the reason that it's negative is because the spring is resisting the change in motion. So if I have a positive displacement and pull the spring out, then the force is going to be in the negative direction, pulling it back into equilibrium. And vice versa, if I push the spring having a negative displacement, the force wants to go back in the positive direction, returning it to equilibrium. Furthermore, the energy stored in a spring is given in the form half kx squared. And this is because energy is equal to the negative integral of force with respect to position. So if you integrate it, you'll get half kx squared. Now, the question arises, how do we know what x is, right? So if I push an object, sorry, let me clarify a bit more. If I have a block on a spring on a frictionless table, and I extend the block just a little bit, what's going to happen is that it's going to get pulled back into equilibrium. However, when it gets pulled back into equilibrium, it's going to have some velocity as well. So it's going to keep going. And in fact, what happens is that it oscillates back and forth periodically. So how do we find the position of the spring when it's oscillating? Furthermore, how do we find the velocity of the object or the acceleration of the object? Well, if we take a free body diagram of the spring, we see that the only force that's pushing on it is Hooke's law, or the force from the spring. So using F net equals ma, we have that negative kx is equal to ma. But a is the double derivative of x, or the displacement. So we can write this as mx dot dot, which is a symbol for a double derivative, the Newtonian representation. This gives us that the double derivative of x is equal to negative k over m times x. So we need an equation for displacement that follows that the double derivative of displacement is equal to some negative constant times the original function for the displacement. And mathematicians or physicists, whatever, have found that this equation can be written as x of t, displacement of time, function of time, is equal to the amplitude, how much the equation moves, how much the function moves, sine omega, which is the angular frequency, plus phi, which is an offset, meaning that at when time is equal to 0, what position the block is at. And so you might be asking, what is omega? What is the angular frequency? Well, what happens is if you take the double derivative and you get a of t, you get the equation as being negative a omega squared sine omega t plus phi. Thus, that means that the equation can be rewritten as A is equal to negative omega squared x. Thus, this is just lines up with what we saw in the springs. So in the case of a spring, omega is equal to root k by m. Once again, k is a spring constant, and it will be given in prompts. So what's kind of the general gist of this? What I'm trying to say here is when you see an equation for any sort of oscillating object, when you see an equation where the double derivative is equal to negative some constant times x, the angular frequency, which is how many radians the radians that the oscillation undergoes in a second, is given by the square root of that constant. So for springs, it'd be root k by m. Another example of simple harmonic motion would be a pendulum. A simple pendulum is given by a massless string and a mass at the end, which swings back and forth, similar to like a swing of some kind. You might have noticed. You might see this. So this, once again, is oscillation. It's simple harmonic motion. So we need to find the equation for this motion, or we need to find omega for this situation. We know the equations is given as x of t is equal to a sine omega t plus phi. Where once again a is the amplitude, how much it swings by. Omega is the angular frequency, the number of radians it goes through in a second. And phi is the offset. So when time is equal to 0, what position it's located at. Thus, we need to find omega. So if we once again draw a free body diagram, we'll see that gravity acts downward and tension acts upwards, or in the direction of the spring. So what can we do? We can use the formula torque is equal to I alpha. And torque is equal to the sum of the forces times distances on the spring. Or on the pendulum. So you might be saying, how can we do that? Let's say that the string has length L. And it's offset by an angle theta. That means the torque on this system is mg L sine theta is a net torque. So this is equal to I, which is ml squared in this case, times alpha, which is the double derivative of theta, or angular displacement. So canceling it out, you get that the double displacement of theta, and sorry, this should be negative because it's a restorative force, is equal to negative g by L sine theta. Now you might be saying, this looks similar to the last situation, but it's sine theta. What do we do with that? So in physics, there's something called a small angle approximation, which means that at small enough angles, you can, the sine theta functions the sine theta function looks exactly like a function of x. So sine of x looks just like x at small angles. So what I'm trying to say is sine x is roughly x, and this is in radians, not in degrees. So if I had a graph of sine x and x, you see that this is what sine x looks like. Sorry, other way around. This looks kind of linear here. And if you zoom in and x is small enough, it is close enough to a linear line. This means that we can replace this situation or this equation with this equation, negative g by L theta, which is it's roughly equal. This, of course, gives us that omega is equal to g by L. Or sorry, it's root g by L. Now, before we get to problems, there's some other things, minute things we need to talk about. Problems will also ask you for normal frequency and period. Frequency, which is denoted by F, is the number of cycles per second. How many times it completes something in 1 second. And as you all know, there's 2 pi radians in one cycle. Therefore, F is equal to 2 pi omega. Sorry. Omega by 2 pi. Whoops. Because omega is the number of radians, and in every radian, 2 pi radians is a cycle. So if you want to divide by 2 pi to get the number of cycles per second. And the cycles per second is also called hertz, which is a unit of frequency denoted by Hz. T, on the other hand, stands for period, which is the number of seconds for one cycle to happen. And this is 1 by F, which, as you know before, or which we have seen, is given by 2 pi by omega, just by flipping this equation. Now let's move on to some problems. So just a quick problem that we could do is a spring. That's my computer's being weird. With the mass attached to it. And let's say this has a mass of 2 kilograms. And then we displace it by 0.01 meters. Now the question is, what is the speed of the block, the highest speed of the block, and what is the angular accelerator, or the angular frequency? So to find the speed of the block, we have to find the total energy that is in the block. So when I extend it by 0.01 meters, the energy I've given is half kx squared. And sorry, let's just say that k is 100 newtons per meter. So the energy I've given it is half kx squared, which means that its total energy is half times 100 times 0.01 squared. So in this case, this would be 1 over 200 joules is the total energy. So at its maximum speed, when it's in the center, none of the energy is stored in the spring because the spring has a displacement of 0. It's at its equilibrium state. So that half mv squared is equal to 1 over 200, which gives us that v is equal to 1 over 200. Sorry, v squared is equal to 1 over 200. So v is equal to square root 1 over 200, which is equal to 1 over 10 root 2 meters per second. Kind of slow, like really slow, but that's because we didn't give it too much energy. The next question is, what is the angular frequency? And that is simple application. Omega is equal to root k by m. Thus, the angular frequency is root 50 rad per sec. Okay. Next question. So this question is about a spring with a spring constant k. Again, it's not letting me draw a spring for some reason. And the question is, if the spring is cut in half into 2 springs, what is the spring constant? So I'll call this KO. And this is K. What is the spring constant of each half? So the way to think about this is that the tension throughout the spring, if I extend this by some distance x, the tension in the spring, it has a magnitude of kx, or k naught x. Each half must have the same tension, because the tension is same throughout the spring. But each half spring only moves x by 2 distance. So what we get is that k, which is unknown, x by 2, is equal to k naught x. Thus, the spring constant of the new spring is equal to 2 times the original. And vice versa, if two springs of the same k are added together on top of each other, they are halved. So yeah, more generally for springs, let's just partition this off. More generally for springs, if you combine springs with different k values, so this k1, this k2, if you combine them on top of each other, then just like capacitors in series, the equivalent k is equal to 1 over k equivalent is equal to 1 over k plus 1 over k. Meanwhile, for parallel springs, meaning you have a block and you have multiple springs connected to it, like this k1, this k2, then it's just like capacitors in parallel. K is equal to k1 plus k2, etc., etc., etc. Okay, the last question is about physical pendulums. So you might be asking, what is a physical pendulum? A physical pendulum is a pendulum that is not just a string and a mass. It actually has weight, it has a moment of inertia. So we're going to be looking at a general shape with some pivot here, and it has an eye around the pivot. So when this is tilted by some very small angle theta, we get the equation that mg theta, using the small angle approximation from earlier, is equal to I alpha, which is equal to I theta double derivative. So MLG. Thus, skipping a couple steps, we get that the angular frequency is equal to mgl by I for a physical pendulum where I is the moment of inertia around the pivot. And this also works for a normal pendulum with just a mass and a string, because I for that is just ml squared, and you'll simplify back to the g by l. Anyway, that's it for this Professor Z video. Please watch the next one. Thank you, and like and subscribe.